Hello and welcome back to Introduction to Green Process Engineering. In this video we will learn about a wood-based bioeconomy. In addition to agriculture, the bio-based economy also affairs forestry, the wood and paper industry, the chemical and particular the plastic industry, the pharmaceutical industry and even the energy industry. The wood-based bioeconomy ideally uses the raw material wood, meaning trunk wood, crown wood and, if necessary, stock wood and waste wood from previous use. Here, the refinement steps are refined further and further through chemical decomposition and modification of materials, and byproducts from the previous steps are used for the next stage. Only at the end of this process it is sensible to use the residual materials as an energy source. However, the primary goal is the material use of wood, for example, for construction, housing or paper, and associated CO2 storage and substitution of fossil materials. As one good example, we can see Canada's forest bioeconomy strategy on the slide. In recent years, significant efforts have been made, especially in Scandinavia, South America and New Zealand, to either further develop the well-known areas of application for wood as a raw material or to develop completely new ones. Developments of the use of lignin for the production of carbon fibers or application research or nano or microfibrillated cellulose for barrier coatings and pharmaceutical application, among others. The textile sector can also benefit sustainably from the wood bioeconomy as new cellulose spinning processes for fibers like tencel with significantly improved properties. The overall view on the structure of the secondary and primary wall within the plant cell wall can be seen on the figure. The principal distinctions are within the constituent regions as well as the cellulose microfibril orientation, as well we can see on the slide. Also, transmission electron microscopy images of cellulose nanocrystals and cellulose nanofibrils and chemical structures are presented. Atomic force microscopy images show how the primary wall consists of ordered microfibril layers. The figure also presents a schematic model as follows: biomechanical hotspots in red, cellulose microfibrils in blue, pectins in yellow, and xyloglycans in green. We can also distinguish between the molecular structures of the main cell wall polymers, hemicelluloses and lignin structures. A very nice presentation of the overview of fibrillated cellulose and its roadmap technologies can be seen well on the figure. Several common source materials of fibrillated cellulose as well as schematic description of the hierarchical structure and manufacturing challenge of fibrillated cellulose are also presented. The forecast of the total production value of wood-based products in the Finnish bioeconomy is used here as an example of the possible impact of the new advanced materials. It includes those from fibrillated cellulose, a roadmap of fibrillated cellulose technologies, including Karin application in paper, near-term application in specialized packaging, bioplastic, lightweight structural materials and energy-efficient buildings and transportation, as well as far-term technologies including novel membranes for energy and water, optoelectronics and bioengineering. As mentioned before, we can also process chemicals from wood-based biomass. We can see that just as the petrochemical industry is based on a relatively small number of about 20 so-called base chemicals derived from oil components, a bio-based industry could be based on a small number of building blocks, so-called platform molecules derived from biomass components. The concept of catalyzed defunctionalization of biomass is opposed to catalyzed functionalization of fossil resources towards platform chemicals is shown well on the figure. In this video, we learned about wood-based bioeconomy, areas of wood-based biomass application, wood-based cellulose cell wall and its supramolecular structure, and fibrillated cellulose nanostructures. Thank you for watching.